So the difference between initial and equilibrium concentrations is related to both the stoichiometric coefficients in the balanced chemical equation, little a, little b, little c, little d, and the number of reaction events that occurs between the initial state and the equilibrium state. We've called that x. To organize all of these different values, the initial concentrations, the equilibrium concentrations, and the change in initial concentrations that leads to equilibrium, we use a device called an ICE or a RICE table. And it's really an organizational device that helps focus our thinking and organize the important values for equilibrium problems as we solve them. The R in RICE stands for reaction, and you don't always see this in examples of ICE tables, but it's very important to use the balanced chemical equation when solving equilibrium problems, which is why I like to include the R when thinking about solving equilibrium problems using an ICE table. A well-organized way to solve equilibrium problems involves using a tabular approach. For each reactant or product, we can write the equilibrium concentration as an initial concentration which is given to us, these given initial conditions, plus or minus the change in concentration which we deduce from Q versus K and stoichiometry. So for example, we start with the balanced chemical equation at the top, and this is the R portion of the RICE table, the reaction itself. We then write initial conditions which are going to be given in a problem's context. So we'll have some concentration of A initial, some concentration of B initial, some concentration of C initial, and D initial, and C and D may be equal to 0, but assuming all of these appear in the equilibrium expression, you should write down equilibrium concentrations for all the species involved, even if they're 0. That's just good practice. The next line is the C line for change. Each change is going to involve this unknown number of reaction events x, but the actual number of moles of each reagent consumed or produced depends on two things: Q versus K, and the stoichiometry. Q versus K figures in because that dictates which direction the reaction will go. Let's say, for example, that in a hypothetical case, Q is less than K. That means that the reaction will go forward. On the other hand, if Q is greater than K, that means that the reaction will go in reverse. For now, let's work with the example of Q less than K, in which case the reaction will go forward. In that case, we can conclude that moles of A and moles of B will disappear, hence there should be negative signs on the change for A and B, while molecules of C and D will appear, and so their changes should be positive. Since the number of molecules actually consumed or produced is scaled by the stoichiometric coefficient, we multiply each of these by the corresponding stoichiometric coefficient. So negative AX, negative B times X, positive C times X, and positive D times X. Finally, to write the last line, the equilibrium line, we simply sum the two. The initial concentration of A minus the change in the concentration of A. The same thing for reagent B, same idea for reagent C where we're adding now, and finally the same idea for reagent D where again we're adding since moles of D are appearing because the reaction is going forward according to Q less than K. There's a key condition on each of these four equilibrium concentrations. And since there's only one unknown variable here, the variable x is the only unknown, we can solve this condition to solve for x, the number of reaction events that occur between the initial state and the equilibrium state. So here's all of that information just organized in a tabular form. One important thing to realize about the ICE table is that there's nothing too profound about this process. We've noticed the impact of stoichiometry on the changes in moles and molarity of the reactants and products, and we've looked at the importance of Q versus K in identifying the nature of that change line. That's really the trickiest part, honestly, about laying out an ICE table, is laying out the details of the change line. Equilibrium is simply the sum of the two, and the initial line will be given to you. You may need to think in some cases about the nature of the system you're working with to generate the initial line, or you may need to do some stoichiometry calculations, for example, to figure out molarities, but for the most part, these will be straightforward calculations that we've already done before. Point is, you've already seen all of the mathematical manipulations necessary to lay down an ICE table. The trickiest part of this is understanding what you know and what you don't know, and how, for example, Q versus K and the stoichiometric coefficients play into the different cells of the ICE table. So here's our ICE table, and initial concentrations will almost always be calculable from the statement of a problem. There are some types of problems, however, where you will start with an equilibrium constant and a set of equilibrium concentrations and actually back calculate initial concentrations from the equilibrium situation. Problems like this will be fairly rare in your general chemistry class, but I can tell you as a laboratory coordinator who has to make sure that the equilibrium concentrations come out the way I want them to, I have to often start with an equilibrium situation and work my way back to the initial concentrations I need to make sure that equilibrium situation actually obtains. Signs of the changes on the reactant and product side will always differ, and that's important. We saw that when we laid out the table previously, but for example, if A and B are negative, then the change in C and D will necessarily be positive, since consumption of the reactants implies generation of the products and vice versa. And of course, knowledge of the balanced chemical equation is essential. And why is that? Because the stoichiometric coefficients appear on the change line, and they're essential for the change line. Let's work through a quick example of applying the ice table approach and finally see how to solve for x, the number of reaction events between the initial state and the equilibrium state, and how to calculate equilibrium concentrations from there. So the setup for this problem is that HCN is a weak acid and undergoes an acid dissociation process in which it surrenders a proton to water to form aqueous Cn- or cyanide anion and H3O+. The problem gives us Kc, we're going to need that at a later stage, and tells us that a student dissolved 1 mole of HCN in 500 milliliters of water. The goal is to write an ice table for this situation, and then eventually we'll solve for x in the equilibrium concentrations. The first stage then is to write the initial situation. Initially we have 1 mole of HCN in 500 milliliters of water, and so this is a nice case where we need to use a little bit of stoichiometry. Dividing 1.00 moles by 0.5 liters of water leads to an initial concentration for HCN of 2.00 moles per liter. The concentration of water is actually irrelevant, and it's irrelevant throughout preparation of the ice table because water is a pure liquid here. Pure liquids don't appear in the equilibrium expression, and since we'll rely on the equilibrium expression later, we don't need to worry about water. The initial concentration of Cn- we can assume to be 0 since the problem doesn't mention the addition of any Cn-, and we wouldn't expect Cn- in pure water. And although we would expect a very tiny amount of H3O+ in the initial conditions in pure water, this 10 to the negative 7 moles per liter, which we'll talk about in a later video series, is so small as to be irrelevant to this situation in which the initial concentration of HCN is 7 orders of magnitude larger than that. So for all intents and purposes, then, we can assume that the initial concentration of H3O+ is 0. We'll talk in a future video series about when it's appropriate to make this kind of approximation and when it isn't. So that's the initial line. Let's move on to the change line. It's very important before we write anything down on this line to assess Q versus K and see where that leaves us. So if we think about Q for this initial state, we have 0 products. So if we plug that into the equilibrium expression, which is the concentration of H3O+ times the concentration of Cn- divided by the concentration of HCN, where we've left the molarity of water out since it doesn't change as the reaction occurs, we see that this has got to be 0 since no products are present initially. That tells us that the reaction is going to spontaneously go forward, and so we can immediately write that the change is negative for HCN, positive for Cn-, and positive for H3O+. And at this point, we can actually write down x, that hypothetical number of reaction events. The last thing to do is to pay close attention to the stoichiometric coefficients, and notice that all the reagents have coefficients of 1 in this case, and so we're simply going to add a leading factor of 1 to all 3 of these concentrations. If those were not equal to 1, we would need to multiply by the stoichiometric coefficients on the change line. Finally, to generate the equilibrium line, all we need to do is simply add the initial and the change lines. So for HCN, at equilibrium, we'll have 2.0 minus x. We'll have plus x for the Cn- concentration and plus x for the H3O+ concentration at equilibrium, and we're done. Here in a second, we'll see finally what the fundamental criterion is on these 3 concentrations. And if you've been paying attention, you probably have a pretty good idea of where we're going with this already. But really quickly, let's debrief this problem to see the important aspects of writing an ice table. Firstly, we saw a great example in this problem of using stoichiometry to determine the initial conditions. stoichiometry may be involved unless concentrations are given in moles per liter, which they often are. It is very important, before writing the change line, to assess Q versus K. In this situation, we had Q less than K, and this is a common situation because when products are not present in the initial conditions, Q is equal to 0, and that tells you immediately, since K must be greater than 0, that Q is less than K. However, that's not always the case, and there are plenty of situations where the initial Q is actually greater than K such that the reaction runs in reverse. Furthermore, this can make your life easier in situations when the initial state is already an equilibrium state, when Q is equal to K. You can immediately stop and say that I've already achieved my goal of finding equilibrium concentrations because Q is already equal to K in the initial state. To generate the change line, we just multiply X by the corresponding stoichiometric coefficients and choose the right sign for each change using the Q versus K conclusion. Finally, to generate the equilibrium line, we just add the initial and change lines. That's all there is to writing an ice table. What do we do with these equilibrium concentrations once we've got them on the E line? Well, this is the essence of solving an equilibrium problem, and it uses the key condition on any chemical system at equilibrium, which is that the equilibrium expression is equal to K, the equilibrium constant. In addition to writing these expressions for the equilibrium concentrations, we can also write that Kc is equal to the concentration of Cn minus at equilibrium times the concentration of H3O plus at equilibrium divided by the concentration of HCN at equilibrium. From the equilibrium line, we have expressions for all three of those in terms of X, the number of reaction events. So we can write for Cn minus at equilibrium, X, we can write for H3O plus at equilibrium, X, and we can write for HCN at equilibrium, 0.5 minus X. Furthermore, and this is the last key piece of information, we know what that expression is equal to, the equilibrium constant for the reaction, which is 7.94 times 10 to the negative 10 in this case. From here, this is just a matter of algebra, solving the equation x squared divided by 0.5 minus x is equal to 7.94 times 10 to the negative 10. You can multiply this out and use the quadratic formula to solve it, or what have you. And really the hardest part of equilibrium problems you'll find is getting to this point and writing down the proper expression for Kc. Solving for x is relatively trivial, and with a calculator in this day and age is relatively easy to do.